Robustness, robustness, robustness. Any guesses about what we're talking about today? Today we have a very special guest coming all the way from the South, Jimmy DeLang. Howdy y'all, pleasure to be here. And by the way, I am 100% permitted to make fun of the South. Why? Because I lived in Oklahoma, y'all. All right, with that, let's talk about robustness. So what do you do when the assumptions of linear models are not met? So let's talk about an applied problem. As y'all know, I want to be a world famous author by my book, The Nexus Has Fallen by Dustin A. Fife, available on Amazon, science fiction, epic. So I have heard from pundits in the industry that there is an inverse relationship between the number of sales and the price of the book. So the more expensive the book, the more sales. Now that seems pretty counterintuitive to me, and my book is 99 cents. So am I kicking myself in the foot? Is that a phrase? Am I kicking myself in the foot? That sounds weird now to me. I don't know. So I know publishers control the price of novels, and as we know, publisher has a small effect on book sales. So let's go ahead and control for that. So research question. Once I control for publisher, do higher book costs lead to higher sales? So you see how I just did the first step in the 8 steps of data analysis? Pretty good, huh? So you understand the rationale behind what I'm doing and the exact research question. But we've got a problem. Like, look at the graphs on the right. WTF. What's the function of selling a $2,429.98 book? Okay, I know that was a stretch. What's the function? Like, what's the purpose? Why can't you just say what's the purpose? Because it doesn't work into WTF, that's why. But there's an even bigger problem. We've got 0 inflated data. So the mode happens to be at 0. And if you want to see how these plots were created, look at the bottom left. I use the uni.plot function, but you could have used the flexplot function, which would work just as well. Now let's look at the bivariate plots. So let's delete those who charge more than $20. Now this is an intentional decision based on theory, because I don't care about generalizing my results to those who charge more than $20, because I am not going to charge more than $20 for my book. So again, I'm using theory and rationale to delete those outliers. Bottom left is the code to generate the plot on the right. And that's not very clear, is it? Okay, there's a lot of different colored dots and hard to see what's going on. And in addition, we don't quite know what the relationship is saying. So p-values, well, these results are totally meaningless. Not because we have p-hacked yet, but because the model doesn't even make any sense. We looked at the data, they're just so wonky that it doesn't make sense to compute a p-value, because p-values assume that we have met the assumptions of the linear model. But in case you're interested, that's how you would compute the estimates, and those estimates don't make sense either. So yeah, we got problems. The data are not normally distributed, we have extreme outliers, the data are not homoscedastic, the data are not linear. By the way, if you tend to violate the assumption of linearity, usually you violate all the others too. So this is a problem. Why? Because the model is just wrong. You know, a lot of people talk about the assumptions of the linear model in terms of type 1 versus type 2 errors, and saying, oh, if you violate the assumptions, you might inflate type 1 error rates. And I suspect that most applied researchers don't care. They just kind of roll their eyes and say, whatever, I'm going to keep doing what I want. And my response to that is, but shouldn't you care about having the right model? That's the take-home message. So checking assumptions isn't about just maintaining alpha levels. What it's about is determining whether your model actually makes sense. So at this point, looking at the graphic, I don't trust the predictions from this model. So if it says I should charge this much money, I don't trust it because it doesn't fit the model, or the model doesn't fit the data. So, oh, I kind of already said this. So, again, your model is wrong. It makes no sense to use that model. It's like, actually, I thought of a better metaphor. It's like going on Amazon and ordering a hammer because you need to pound something, and then they send you a table saw. Absolutely nothing wrong with the table saw. I have a table saw and I love it, but you can't pound nails with the table saw. It's just the wrong tool. Okay? Again, nothing wrong with the tool. It's just not the right tool for the job. Likewise, if you're using a linear model, nothing wrong with linear models. But if you try to fit it on data where linear models aren't appropriate, it's just the wrong tool. That's okay. Just use a different tool. All's good. So what do we need? We need models that are not sensitive to outliers. We need models that don't really care about whether the data are bimodal, skewed, zero inflated, those sorts of things. What we need are robust models. All right, so robustness, linear models, when we use them, they assume linearity, normality, homoscedasticity, and independence. So linear models may or may not be robust to violations of these assumptions. That's the problem. So in other words, if we fail to meet one or more of these assumptions, bad things can happen. Like Professor Fife said, type 1 error rates under the null are no longer 0.05. Well, that's a problem. Type 2 error rates are higher than we'd like them to be. And effect sizes and parameter estimates may just be really off. So in short, we have a bad model. And if bad things happen, the model is not robust. So we have a model that assumes these things. We violate those things. If our model ain't robust, we're going to have some problems, see? So how do we assess robustness? Well, typically the literature has operational definitions of robustness, and they operationally define them as the degree to which we deviate from a 0.05 error rate. So, for example, we might simulate skewed data where nothing's going on. So with normal data, how often will we say nothing's going on? Well, we say it 5% of the time if we set an alpha level of 0.05. Well, on the skewed data, what we can do is we can test whether the effect is there. Now, remember, we simulated it so it's not. So let's say we repeat 10,000 times in a proportion, and the number of times normal methods and count the number of times normal methods say there's something going on. And if that proportion deviates quite a bit from 5%, we got problems, see? So would you care to see an example? So I actually ran a simulation here to see what happens. And so if you look at the top graphic there, that shows you the distribution of the data. Now clearly, we have some problems with normality here. These data are zero inflated. They are severely skewed. We should not be using t-tests. But let's go ahead and run the model, and if we do that 10,000 times under the null hypothesis and compute, let's say, what is that there? Are you robust? Oh, so that's looking at the Cohen's d. And so if we were to compute the Cohen's d over these 10,000 iterations, what we find is that if you look at the bottom graphic, the distribution centers around 0. Now remember, the data were simulated such that 0 is the answer. And so the fact that they're centered around 0, that's very promising. So it seems to us that our estimate of Cohen's d is very robust, which is good. Okay? Again, we violated the assumption of normality, and things turned out just quite all right. Quite peachy keen. As right as rain right there. So what does the literature say about the robustness of linear models? Well, there's some debate. So for example, some say models are not robust in general, but that really depends. What's your sample size really? What procedures are you using? Are you using a t-test? Are you using a regression? Regression tends to be less robust than a t-test. What assumptions are you violating? And how are you defining robustness? Are you defining it as a type 1 error rate, type 2 error rate, the deviation from optimal effect size? So it really depends on what's a researcher to do. That's the question. Well, the single best thing you can do, thank you for that. That was an excellent explanation. So the single best thing you can do is identify the conditions of your study. Well, really, the conditions of your study are going to be unique. And so there's no secret formula to determine whether your model is robust or not. So the thing that you can do is try a robust version of your model. And what do we call this again? Oh, we try a robust version of your model, try a non-robust version of your model, and then compare the two. And what do we call that? That's called a sensitivity analysis. Now remember, in the 8 steps data analysis paper, I talked about 3 guiding principles, and one of those guiding principles is sensitivity analysis. So if the results differ, then you can worry about it. If they don't, you're good, easy peasy. And by the way, Erseg, Hearn, I have no idea how to say these people's names. They mention in their paper, hopefully you all have read it, about sensitivity analyses, and their basic point is, yeah, you can run a sensitivity analysis, but the problem is robust models, if we do not violate any assumptions, they give the same results as non-robust models. So if you're going to run both anyway, why not stick with the robust versions? And so they argue that you should always just use robust versions. And that is actually not true, and you'll see why that is in a few minutes. So there are 4 methods to robustifying estimates. 1 is that we can do transformations. 2 is that we can use nonparametric or rank-based procedures. 3, we use trim means, Winsorized variances, and bootstrapping. And then 4, I don't know that those would technically fall under robust methods, but I'm going to lump them in because we're trying to address the same problem, which is to use generalized linear models. So all these may robustify your estimates. That is, your estimates will be about the same regardless of whether the assumptions are met, but there is a cost. So we will likely lose the metric of the variables. So for example, if you transform or use nonparametrics, and oftentimes generalized linear model, well, actually, no, that's the next point. So if we will lose the metric. So for example, I might want to know how much more money I will make per dollar increase in my book. Well, if you transform your variable, you can't really tell you that, but maybe I could tell you how much the log of the money increases. Now, of course, you could always go back and convert it back into the raw values, but it's not linear anymore. So the difference between 99 cents and $1.99 is not going to be the same as the difference between $1.99 and $2.99. Also, another cost is you may lose the ability to compute effect sizes in a familiar metric. So trim means so far, for example, don't allow you to compute effect sizes in familiar metrics. Generalized linear models. Also, nonparametric procedures. So you can't compute a Cohen's d using nonparametric procedures, for example. And finally, you may lose the ability to compute p-values even. So GLIMs, at least in R, GLIMs we'll talk more about that later, but they don't naturally report a p-value. And sometimes the trim means don't report p-value. And at the very least, even if we can't compute via p-values, the meaning of significance is much less clear than it is with simple models. So in other words, step 4 or 5 of the 8 steps of data analysis may not work, or even step 3. Eek, that's a problem. All right, so p-values on complex models. So we'll see this issue when we talk more about mixed models and generalized linear models. So basically, to compute a p-value, you need to know several things. You need to know what the distribution is that you're comparing it to. Well, once we robustify things, that distribution becomes unclear. We need to know the variance of the parameter. Again, once you start messing with things, this becomes unclear. And let's say we do know the distribution, we still need to know the degrees of freedom. Again, this becomes unclear. And the end result, the p-value may not be 0.05 anymore, people. So R is very good about being careful about reporting results, often at the cost of frustration to the user. So if there is not a definitive answer on what the meaning of a p-value is, R tends to not provide an answer at all. And this has been very frustrating to people in the past. So however, package maintainers like me are ever willing to provide an answer, even if there's no consensus on how the answer should be computed. So if you're doing generalized linear models, for example, it won't compute p-values, but there are packages out there that compute p-values, but hopefully you recognize that those p-values may not actually make sense. And as y'all know, I don't think p-values make sense anyway, but discussion for another day. So that same problem exists for effect sizes too. Ask me how I know, because I've tried to compute effect sizes. For example, if we want to compute an R-squared on a trim data set, do we only count the residuals? Because remember, an R-squared is a measure of, it uses the residuals to compute R-squares. So do we use do we only count the residuals of the trim data set? If so, we are artificially inflating the R squared because we're getting rid of the outliers. Or do we include those outliers and reduce our R squared? Again, in this situation, there is no easy answer. And in cases like this, R generally remains silent. And if you want to read more about this, there's actually a very fascinating discussion among statisticians and other people on that link right there. So robustness, pros and cons. So the idea of robustness is great. We can run a model and it will give us estimates that don't change even with extreme outliers, non-normality, homoscedasticity, those sorts of things. But you can't have your cake and eat it too, as they say. Once we robustify things, we lose many of the beautiful advantages of GLMs. Now notice these are not generalized linear models, these are general linear model. So everything we've done so far have been general linear models, t-test, nova regression, those sorts of things. So once we robustify, we lose R squared, we can't do Cohen's d, and the p-values may become less meaningful. So what do? Again, going back to what I was saying earlier, we run the results before and after robustification, then we pray and hope and wish that things don't change at all. Otherwise, we will most likely have to sacrifice something that is naturally intuitive to us. And of course, we must be explicit about our choices, defend them wisely, and invite your audience to evaluate your decisions. So going back to that paper, like I said, those authors earlier said that if you're going to compute the robust version anyway, why not just stick with the robust version since it's always going to be as good or better? Well, if you do that, you lose some of the intuitive metrics, and that's a problem. Now on to some transformations. So what are they? Well, Tukey called them re-expressions is all. We take the original variable and re-express it using some mathematical function. So income, for example, may become the log of income, the square root of income, or 1 over income. And so what we then do is we then try to predict the re-express variable. And this always bothered me when I was younger. It seemed like p-hacking to me. Aren't you in exploratory mode now? Well, probably, because you're going to yield different p-values when you modify these things. And your original data don't seem to fit, so we just make up new data. So it does? Well, this seemed kind of shady to me, you understand? Well, actually, transformations are okay. Now remember, in stats, we're not really interested in the variables themselves per se. What we're interested, well, we are, but insofar as we're interested in the relationships between the variables, you understand me? So transformations preserve what we call monotonicity. That's just a big fat fancy word for saying one variable, if it was higher than another before transformation, it's still higher than another after transformation. So for example, if Joe was the highest and Samantha was second highest, the order will still be preserved. Now there's that little footnote there that sometimes, like if you're doing a inverse transformation, Joe becomes the smallest rather than the largest value, and that's okay. It's still monotonicity is maintained. So however, what is different is the size of the difference between Joe and Samantha may differ. So before transformation, the difference might have been huge, but after transformation, maybe the difference is much smaller. So we're still predicting who's highest, second highest, etc., but we're coercing the data to be more normal so we can use approximately 200 years of statistical theory to our benefit. That's the basic idea behind it, and so that's why transformations are okay. But again, there is a little bit of an element of exploration in there, and that's okay as long as you're explicit about it and you don't use any p-values or anything. So let's go ahead and try that. Let's say if we do the log transformation, oh, by the way, we have to, if we do a log transformation on these data at least, we have to add 1 to y because you can't take the log of 0. Okay, you understand me? If you try to take the log of 0, it's going to give you a value of negative infinity, and that just ain't right, you understand? So what is a log and what does it mean? Well, it tells you how many times we'd have to exponentiate 2.718, which is the natural log, to get that value. So for example, let's just say that our book sold 7,000 copies. Well, if we take the log of 7,000, that gives us a value of 8.85. And so what that tells you is we would have to exponentiate 2.718, which again is the natural log, 8.88 times to get the value of 7,000. Oh my goodness. Did you really have to tell? I'm recording a video right now. Can't you remind me later? And I hope it's much later, because quite frankly, I find that very annoying and very offensive. My goodness. All right. So back to what I was saying. So you would have to exponentiate 2.718 8.88 times to get 7,000. So for example, we would say 2.71. Oh, I changed it from 8 to 6. Okay, that's supposed to say 2.718 times 2.718 times 2.78, etc. You do that 8.88 times, and what does that give you? Well, that gives you 7,000. Understand me? So the log of 7,000 is 8.85, which basically means if you multiply, or if you exponentiate 2.718 8.85 times, you would get 7,000. Does that help? Well, does that help understand? Hopefully you understand what that means. So now let's ask whether it helps with the data set. Well, it's more normal among who did not score 0. But remember, if everyone has the same score, they still have the same score, because we're preserving monotonicity. And so if you have 0 inflated data, then any amount of transformation ain't going to do nothing. Okay? You've got to resort to other methods here. But that, so like I said, transformations, there's nothing unethical about them, but that don't mean there's no cost. We lose the interpretability of the parameters. So let's say we were to run this model, even though we got 0 inflated data. So parameters are now on the log scale. So sale price, for example, says for every $1 increase in the price of my book, we expect the log of sales to decrease. Oh, that's interesting. We expect it to decrease by 0.038. But of course we can convert that back to dollars, but only for a particular price point. Again, why is that? Because the slope changes for different price points. So in this example, if we were to exponentiate the prediction, if my book price were 99 cents, it would guess that I would sell 13 copies, or let's see, is the dependent variables? No, it's in, well, sales, I don't know if it means dollars, how much money I'd make, or how many sales I'd make. I can't remember, I forget. So anyway, let's just say it is books sold. So that says that it would predict 13.54 books if I set the price at 99 cents, whereas if I set it at $1.99, it says that I would be making $13.03. And if I set it at $2.99, I'd be making $12.55. That makes sense. And what about the bivariate plots? Well, if we were to plot a bivariate of the distribution after we did the transformation, well, this very poorly models those who aren't making sales. It does okay for those who make a little bit. Well, really, I guess it poorly models everything. And it's a little messy. We'd have to do some cleaning up there, but you get the basic idea. So if there is so this is a common problem with 0 inflated data. Rarely, or I might even say never. I might be definitive here and say never. If you got 0 inflated data, it's never going to work. Okay? So rarely do transformations work. Very good, thank you. So choosing among transformations, I showed what would happen if you were to log the data, but there are others. You can use Tukey's bulging rules, or as the crafts like to call it, Tukey's bulge. And it's basically a heuristic for identifying what sorts of transformations you can use to straighten out the relationship between X and Y. But a better alternative that is post-Tukey is called the Box-Cox transformation. And a Box-Cox transformation basically takes all the guesswork out for you. You don't have to remember any sort of rules of thumb. Basically, you give it your model and it will tell you how best to transform the dependent variable. But I'm not going to do that. If you want, I can help you outside of class. But generally, I'm not a big fan of transformations. I think it makes more sense to use one of the other strategies. So in summary, transformations can make the data well behaved, but there's a problem. They won't work with 0 inflated data. They change the interpretation of parameters. And again, let me emphasize this repeatedly. At this point, we are in, I should probably say we're in rough CDA mode. I wouldn't go full on exploratory, but we're in rough CDA. So non-parametric approaches. So these are very common in biology and frequently taught in textbooks. Unlike transformations, they essentially convert all your scores to ranks and attempt to determine whether, for example, average ranking differs between groups, or the correlation between ranks differs from 0. And there are effect size measures that compute the probability that a randomly selected score belongs to group A. I think that's generally the interpretation of it. These are very, very dated procedures, though. They're not very robust to heteroscedasticity. Apparently, I haven't done much research in it, but that's what I've read. They completely change the interpretation of parameters, again, because everything is converted to a rank, and they're not reversible. So basically, if you convert something to a rank, you can't go back to the original scores, whereas you can with transformations. The biggest problem that I see is that once you go beyond very basic statistical procedures, such as ANCOVA, factorial ANOVA, multiple regression, etc., there are no equivalents. So, non-parametric equivalence of an independent t-test, that's the Mann-Whitney U. Of a related t-test, we call it the Wilcoxon. Of an ANOVA, we call it the Kruskal-Wallis. And of regression, we call it the Spearman, kind of, sort of. Spearman's more of a correlation than regression, but yeah. So, reminder, we choose a graphic that matches our analysis. Hopefully, I have made that point repeatedly. It doesn't make sense to do a graphic that doesn't match your analysis. So if we're converting to ranks, then it doesn't make sense to display the wrong data. We should instead be displaying the ranks. Now when I worked as a biostatistician, by the way, that's where the 7 steps, or actually there are 8 steps now, that's where this began, was when I worked as a biostatistician. Because people would frequently compute a Spearman correlation and then show the scatter plot of the raw data. And in my mind, that just doesn't make sense. Why would you display, because the graphic doesn't match what you did in the analysis. And so that plot at the right, called a Spearman plot, I believe I invented that. I don't know that I've seen anybody else, but it basically shows the relationship between the ranked variables, and then in the off axis, it shows the distribution of the raw data. But in this situation, even a Spearman plot doesn't make sense. It just looks wonky to me. And then there's random forest. Remember, random forests are non-parametric, so they don't give a stinking hoot about how the data are distributed. But the same limitations apply as before. So random forest is a black box, and it's a bit tough to visualize, at least without Pfeiffer. And it has some, as well as some other statistical packages. There are other packages out there that help you visualize it. But there are other limitations. So random forest now has to be cross-validated on a new data set, which is, I don't know that that's a limitation. I think that's a strength, that it's encouraging you to replicate. And again, at this point, we are in exploratory mode anyway, or rough CDA anyway, so I don't see that as a big deal. So with that, let's go ahead and look at a random forest prediction. So this is using the compare.fits function, and the red line is the regression, and the, I guess that is kind of an aqua color, is the random forest. And so random forest is more sensitive to where the data are actually at, and it's doing a lot better. I'm not sure that it's quite accounting for the zero inflated nature. I think the predictions are a little bit high, but it's certainly doing a lot better than a linear model. Linear model even predicts that you're going to make negative, which doesn't even make sense. All right, so now we get into modern robust methods. So here's the logic behind modern robust methods. We've got hundreds of years of statistical theory backing the way we do things now. So let's not reinvent the wheel. Let's just make robust versions of existing statistics. So instead of means or conditional means, we use trimmed means. So instead of variances or conditional variances, we use Windsorized variances. And instead of computing p-values based on distribution theory, we compute it based on bootstrapping. And then once we do that, we can use the same machinery as before. So what are the robust versions? Well, a trim mean, basically what that means is we compute the mean of the middle 80%, for example. It doesn't have to be 80%, it might be 60%, it might be 90%. But basically, we compute the mean in the middle of the distribution. And we delete 10% from the top and 10% from the bottom. So some research suggests that 20% is optimal at balancing losing power, because you're losing sample size, but you're also getting rid of the outliers. So there's some person who at some point, it's probably, I don't know, it might be Windsor, can't remember Windsor's first name, but anyway, there's a trade-off, and it seems that about 80% is the optimal. And then there are Windsorized variances, which are similar to trim means, except we don't delete the top and bottom 10%. Instead, what we do is we replace the bottom 10% with the value that corresponded to the 10th percentile. And likewise, we do that with the 20th percentile. And so then we compute the variance as before, except so remember, in a variance we compute the deviation from the mean, but this time we compute the deviation from the trimmed mean. And now those bottom 10% all have the same value, and that's what we use to compute the variance. And then bootstrapping. So with all this data manipulation, we've screwed up the sampling distribution, so it doesn't make sense to compute p-values anymore. But we would still like to get a distribution in order to compute p-values. So what we do is we make up a new sampling distribution. So just a quick explanation of what bootstrapping is. So with bootstrapping, we assume our sample is a random sample from the population. And if that's the case, therefore, we can randomly sample from our random sample, and that bootstrapped random sample is itself a random sample from the population. Does that make sense? So think about that for a minute. Again, we are sampling from our random sample, and that sample from our sample is itself a random sample from the population. But there's a difference. We are sampling with replacement. And what that means is, let's say in our original sample we have Tom, Jill, and Dimitri. And if we were to sample with replacement of size 3, we might sample Tom, Tom, and Jill. So Tom gets selected twice and Dimitri doesn't get selected on that iteration, but then we do it again, and then maybe Dimitri gets selected 3 times the next time. And so we do this repeatedly. So for example, we might do 1,000 times, and at each iteration we compute the trim mean and the Windsorized variance, and then we compute confidence intervals based on an empirical sample. Or in other words, we can say, what is the range under which 95% of the means fall? And does that 95% interval differ between the 2 groups, for example? And then we can use that to then kind of make inferences just as we would a p-value. So the interpretation of the p-value changes here. So before it was the probability of the data belonging to the population null distribution if the null is true, whereas now it means the proportion of times the bootstrapped control outperformed the bootstrapped treatment, for example. Now, criticisms of modern robust methods. So Tukey criticized it and said that you're wantonly throwing away data without any theoretical reason. So when we delete outliers, we should only do it after long consideration of why they were an outlying data point and make sure that we don't care about generalizing to that data point. Now, what you do when you delete 10% of your data, you're inducing selection bias on top of the problem of having outliers. So your sample is no longer representative of the population. So you can only generalize to the center of the data. Well, don't the upper 10% and the bottom 10%, don't they matter too? Well, sometimes they're more interesting than the middle. So I'm tempted to say, for these very good reasons, I'm very hesitant to use robust methods. However, I do like to use them so that I can do a sensitivity analysis. So this informs me whether we need to consider alternatives. So example, before I robustify this, I should consider whether I want to limit my model to only the middle, and I want this to generalize to me. So I probably won't be selling 7,000 books a day, and I'm okay, or $7,000 a day, whatever it is. I'm okay with eliminating the top 10% of the people. But I also don't think I belong to the bottom 10%, I hope. But at the same time, the 10th percentile probably looks quite similar to the 50th percentile. I'm guessing that 50% of the data are selling, or more, are selling nothing. So if you eliminate the bottom 10%, that ain't fixing the problem at all. And yet, I want to know how bad my original estimates were. I want to do a sensitivity analysis. And so doing a robust analysis will tell me how much the outliers are changing my model. So with that, here's the different models. So RLM stands for Robust Linear Model, and that's, I mean, it's very simple to run it. You run it exactly as you would the LM command. And so the red line is the linear model, and the teal line is the robust version, and look at that. it is a whole lot more conservative, at least with the Amazon data, than the linear model is. And otherwise, the predictions look pretty similar, although if we zoomed in, they might be quite different. So now that brings us to generalized linear models. So generalized, we abbreviate with GLIM. So with the previous approaches, we tried to modify our data in some way so it is normal, except with the exception of random forests and the rank-based procedures. So GLMs basically say, screw it, I don't need no stinking normal distribution. So rather than assuming the residuals are normally distributed, it assumes that, for example, the residuals are distributed as a Poisson or count data. The residuals are distributed as, a gamma, which is a skewed continuous distribution. Or you might say my results are distributed as a negative binomial, where this is count data like the Poisson, but it has a bit more skew. Or you might say the residuals are distributed as a binomial, in which case we're using logistic regression. Now this is a topic of later in the semester. Excellent topic though. So pros and cons of GLIMs, they actually do model the outliers. So you can generalize the outliers. If they don't throw data away, that's awesome. They tend to fit the data quite well, provided you choose the right kind of generalized linear model. The problems with GLIMs is that the parameters are often expressed as odds or inverses or square roots or something like that, which means when you're looking at the output and you look at the estimate, it's really hard to interpret what that means. Another problem is that many, if not most, familiar statistics that we use, like Cohen's d, r squared, standardized Bayes, those sorts of things, they don't transfer. So there are not GLIM versions of those statistics. But we can do model comparisons, which we'll get into when we talk about GLIMs. So how about the Amazon data? Don't worry about doing this yet, because we haven't gotten to the point where we can actually model these data. But the teal line shows what happens when we, so this is just using a quasi-Poisson, which is, you'll learn more about this later, but it's like a negative binomial. So we've got the red line, which is the GLM, and then the teal line, which is LM. And so ironically, the Amazon data, it actually predicts more using the GLM than it does with the Amazon data. So that's kind of interesting. But the cool thing about it is that it bends. It recognizes that there's this kind of plateauing that happens as you increase the price of your book, that eventually you're going to fall at zero. So if I were to really investigate this, I would probably zoom in on these. In retrospect, I probably should have done that in the PowerPoint, kind of zoom in to where the fits are going through the data and make sure they are traveling through the densest part of the data, just as a visual inspection to make sure the model is working. So with that, those are the goals and objectives. Hopefully you understand the basics. And I'm not going to review these because this video is already really long. Am I right? Oh, you certainly are, but it's been quite a hoot, quite a blast, quite a lot of fun, and I really appreciate you inviting me on the show here. It's been a treasured experience of mine, and I'll remember it forever. Well, we will remember you too. You've been quite a delight to have here, my friend. Thank you all for tuning in, and we will see you next time.